Welcome. In this session in linear data analysis, we'll explore cross-validation, and we'll explore it specifically for what's called k-fold cross-validation. So let's consider a partition of the data. And let's suppose that we represent our design matrix X as having two parts. Let's call it X1 and X2. And likewise, let's take our dependent vector and partition it so that these are equal sizes. So this will be Y1 and this will be Y2. And what we can then do is we can then train twice. So let's train, and we'll call these models. And what we'll do is we'll say that x1 times a first weight vector is approximately our first set of dependent values. And then what we'll do is we'll train a second model on the second part of the data. So that will be approximately the second part of the dependent data. We can then find the training error as the RMS, as the root mean square errors. So we can say that the training errors are, this would be the root mean square, and the way that we're writing it is we'll evaluate that using design matrix 1, data vector 1, and then we'll put a semicolon and say that we're using weight vector 1. And likewise, we have another training error, which is how good did W2 perform in training on its data. So we will have x2, y2, semicolon, W2. So we're able to train the model twice, and we can get a validation twice of its training errors. Now, what we can also do is we can cross-validate. So cross-validate means that we take these and let's call these our testing errors. And our testing errors are, we can find the root mean square of, so now let's take this carefully. Let's say that we take data set 2, dependent vector 2, and we use the vector from the first training. So we're training on x1, and then we'll test it on x2. Then we can repeat this. We can say, what's the root mean square error using design matrix 1 and data vector 1, but using the model in 2. And in the ideal world, we would like the training and testing errors to both be as low as possible, and we would like them to be as equal as possible. In practice, this seldom happens. And using ordinary least squares, what we often find is a rather annoying behavior, which is we'll frequently find that the training errors are small, and there are good statistical reasons why that has to be. And then it's not unusual at all to find that our testing errors have increased. What this is doing is this, you can think of this as a gigantic leave many out, right? So if what we do is we break this data set into two pieces, first our design matrix and then our dependent vector, and if we break it into two pieces, we're able to carry this on, and we're not just determining how well the model fits its data, we're determining how well the model fits data that it was not originally fit to. So this is cross-validation. Let's go through an animation of this, and then we'll also explore how we can extend this into more than two subsets. We can visualize this process in a straightforward manner. Suppose that we have our first design matrix and our first dependent data vector, and then we have our second design matrix and our second dependent data vector. What we can do is we can train our second weight vector using this second set of data. We can then cross over and we can test it on the first design matrix and the first dependent vector. Likewise, in a second round, we have these two sets of data. What we can do is we can train our first weight vector on the first data set and then cross over and we can test it on the second data set. So each one of these data sets, so the combination of a design matrix and a dependent vector, we call that a fold of data. And you can appreciate immediately that we don't necessarily want to simply take the first half of the data and then the second half of the data. We may want to mix them in. We may want to randomize them. So if we do a randomization, of course, we have to be sure that the rows of the observations and the rows of the dependent data correspond appropriately. Now, can we extend this? I don't see why not. Let's suppose we divide our data into three subsets. And again, we're going to now assume that these are randomly divided. And this now gives us three design matrices, x1, x2, and x3. And it gives us three dependent data vectors, y1, y2, and y3. Now, I'll take those ideas that we had for the two-fold cross-validation and bring it into threefold. And to do this, I'm going to use modulo 3 arithmetic. So I'll say we'll represent the model j plus 1 as using, we'll now combine j plus 1 and j plus 2 data. And likewise on the dependent vectors, we'll combine j plus 1 and j plus 2, and that will give us model j plus 1. We can then cross-validate on j, which is the missing part, using j plus 1. So we'll cross-validate using the design matrix, number j, and the dependent vector, number j. So when we start with 1, which is where in MATLAB that's where we always begin. What that means is we'll compute number 2 using 2 and 3, and then we'll cross-validate on 1. Let's try to picture this. So when we try to picture this, what we get is in round 1, we now have our first fold, our second fold, and our third fold of data. So what we're doing is we'll train our model number 2, and we'll combine the number 2 and the number 3 into one training set. Then we cross over and test it on number 1. In round 2, we take our 3 data, and now what we want to do is train model number 3. And so we combine the data from 3 and the data from 1, and then we cross over and we calculate the test on number 2. And finally, in round 3, we take our 3 folds of data, and now what we'll do is we'll train our first model, and we'll use fold number 1 and fold number 2, and then we'll cross over and we'll test it on fold number 3. And so we can continue this for as many times as we want. Now, this is referred to as k-fold cross-validation, where the number k is the number of folds. And so far what we've done is we've looked at two-fold and three-fold validation. In the literature, typical values are 5 or 10. It turns out statistically that we rarely need more than 10, and practically we rarely need more than 10. I have seen some unusual numbers for k, such as 7, but the usual ones that in the literature that I'm reading are 5-fold and 10-fold cross-validation, and in our context, that's of a linear regression.